Hello, today I'm going to present one of the very attractive project. Today I'm going to present the project which I did one in my Geo Institute, that is cross domain adaptation. Study how adversarial examples generated for one domain affect VITs trained on a different domain. So obviously I will go through this project, but before that I would like to show you where from I have got this idea and all. So obviously there is sorry obviously there is Chrome, ChatGPT and all, but these are the papers I got access from, where I just realized that okay, I can do all these things. And now one of these is adversarial discriminative domain adaptation. So nowadays so much there is an effect, like attacks on different things and perturbations and false attacks, fault images, false even people. So it's like all that, how we can just make it more strong, how just we can make it more robust, and all these things we can include here. So from that I got this idea, and this is the paper, one on another paper, adversarial attacks and defense competition. So here we got the idea that so I performed the FGSM attack for there. So there are many types of attack, like non-targeted attack, targeted attack, and we have the white box and black box models. So uh, there are several kinds of assumptions of the attacker's knowledge. Okay, so two of these are, one of the white box and another is black box. A white box attack assumes that the attacker has full knowledge and access to the model, including architecture, inputs, outputs and weights. And a black box attack assumes that the attacker only has access to the inputs and outputs of the model and knows nothing about the underlying architecture of the weights. So there are also several types of goals, including misclassification and source target misclassification. So the a goal of misclassification means adversary only wants the output classification to be wrong, but does not care what the new classification is. And the source target misclassification means the adversary want to alter an image that is originally of a specific source class, so that it is classified as a specific target class. Okay, so all these things we will go through a detailed and implemented examples for all this. So for that I have my codes and all, which I will obviously share you, make you understand. So so before that, one other thing is, so that I can show you what you can see here. So mainly basically we have two objectives of our project. The first one is adversarial example generation. The objective of our project on adversarial example generation is to understand and implement adversarial attack in machine learning and use these examples to evaluate and enhance the robustness of various models against such attacks. Another is cross-domain adaptation. Here we use the adversarial example generation. This explores the effectiveness of vision transformer in cross-domain adaptation technique. Our study aims to investigate how adversarial example crafted one domain impact the performance and robustness of VITs trained on a different domain. By examining VIT's behavior under understandable adversarial condition, we seek to uncover insights into their adaptability and vulnerability across diverse data sets and domains. So this one, the first one is our adversarial example generation, where we have taken normal CNN, convolutional neural network, and our dataset is MNIST dataset, the handwritten digit, that is our dataset. And we performed here the adversarial attack, FGSM attack, and we created the adversarial examples. And now we will use those examples in the next part. So this is the accuracy versus epsilon. Okay, so epsilon, you can see here that there are various values we are changing from 0 to 0.3, or we can change more. But the thing is, what is epsilon? Okay, so we are going to the attack part only. If we go to the if we consider the attack, okay, FGSM attack, then epsilon is a thing which helps us determine, which helps us making the images more perturbed. Means the variable epsilon represents the strength of the perturbation applied to the input image. It determines how much noise we add to the image to create the adversarial example. So we can detail it more, like small epsilon means that the changes to the imagery are very subtle. The adversarial noise is almost imperceptible to the human eye, but it can still be enough to confuse the model. And the larger epsilon values makes the changes more pronounced. The image may start to look visibly distorted to humans, and while it's more likely to fool the model, it's also more likely to be detected as an adversarial example. So the goal is to find the smallest epsilon that can cause the model to misclassify the image, ensuring adversarial example is as close to the original as possible. So there's a mathematical explanation of this which I have mentioned in my in here. So, well, this is a gradient. Okay, so this will change, and the formula, yeah, this is the formula. This is the formula of the FGSM attack. So this is self-explanable, so I'm not explaining this now. Okay, so the examples have been created. So when epsilon was 0, so 779900, they're detecting right. I have changed a little bit, 0.05. Then it started to identify as a wrong, like 2 to 8, 1 to 3, 3 to 5. So we tried to make this robust. So for that, first we tried using one epoch only. This is the same code, but it's a one epoch version. And this is another code. This is the 5 epoch version. Okay, here. So I will explain this mainly. So this is our final project. There's a cross domain adaptation. So first I have told you that MLSO have integrated it to show the artifacts, the images, the overfitting, underfitting, accuracies and all in a very very cleared way. So okay, I can show you here by running. Let us about this is my previous thing which I got running. Okay, about it. Now, so this is our ML runs one, which has been created from the ML flow pipeline. It is created here. So I will now just run this. Okay, now it's running. Okay, so this is the port where it will be running. So we will see this. So this is the port I was already exploring. So this is the thing which got created. Here you can see that there's a baseline accuracy, baseline adversarial accuracy, fine tuning loss, whatever we have got very very clearly, everything is given. How much hour I've invested even that's also given. So these are the model metrics which I was saying like that. Okay, 0.14, 0.13, the training loss. So here we can see there is slightly on overfitting. So we can see all these metrics, in fact the timestamps, where, which point, everything is very clearly mentioned. And this is the artifact section where we can see everything which has been created and all. This is the ML model. ML, this is our ML model which has been created, is the baseline model. We can register the model, if we know that this is the only model we want to register, so this we can just register a model. We can just register the model like this, and it will come as a registered model. So these are the things you can just explore. I have already shared again and again. I'm telling it's on in my just, I've just given all this so that while you read the report, it becomes more easy. So now let's go to the actual part, that is the code part of our main thing. So here you can see that the top PyTorch and all, they have been imported. Now they have been imported. Now I just saw the images, what it is there in Cypher 10. Then I saw what is there in MNIST. We have taken VIT V16 as a pre-trained model. So why VIT? Why not other model? Even if I have considered CNN while doing this adversarial example part, is they provide us more robustness, transferability. VIT has shown to possess better adversarial robustness when compared with other architectures like MLP, mixed and convolution neural networks. If I say about transferability, VITs have demonstrated stronger transfer to various black box models, including most VIT variants, CNN, and MLPs, even for models developed for other modalities. This means that an adversarial attack crafted for a VIT model can also be effective against other type of models too. So these are obviously better. Feature diversity adversarial perturbation, FDAP, leverages the feature collapse phenomena in VIT, where the critical attention mechanism overly depend on the low frequency component of features, causing the features in middle to end layers to become increasingly similar and eventually collapse. So FDAP naturally accelerates the process and achieve remarkable performance and transferability. Though here the what we have used VB16 architecture is part of Vision Transformer model, which is uh, there in the paper, and image is worth 16 to 16 words. So I have already defined there the links and all. So now basically I will just go to my workflow which I have. Source domain is Cypher 10 and our target domain is MNIST. So okay, if you want to make you understand in a very layman term, then we apply this adversarial example to make the model more robust. What we did is applied the adversarial attack on source domain, created adversarial example, fine-tuned it on target domain, and see how well does it perform in an undomain, that is a target domain. So this is like, imagine you have two photo albums, one filled with pictures taken during the day and another with pictures taken at night. So our day is the source and night is the target. Now suppose you have a friend who is excellent at identifying objects in daytime photos but not as good as when it comes to nighttime photos. This is like teaching your friend to recognize objects in nighttime photos as well as they do in daytime photos. Domain adaptation techniques are methods that help your friend learn from the daytime album and apply that knowledge to understand and recognize objects in the nighttime album, even though the lighting conditions are different. This means making the object in nighttime photos appear more like they do in the daytime photos. So this is aligning the source and the target domain. It's like adjusting your friend's vision to see nighttime photo with a daytime filter so that they can recognize objects better. Now the adversarial training methods with a domain discriminator. Now imagine you play a game with your friend. You show them a mix of daytime and the nighttime photos, and they have to guess which album each photos belong to. At first, they might not be very good at it, but as the game goes on, they get better and better on spotting differences between daytime and nighttime photos. This game is like adversarial training, where the domain discriminator is your friend's ability to distinguish between the two types of photos. The goal is to make it hard for your friend to tell the difference, meaning they have become equally good at recognizing objects in both day and night time. In summary, applying domain adaptation technique and using adversarial training method with a domain discriminator is about teaching a computer model to perform a task well across different conditions or domains, even if it was originally trained in just one condition. Here, we performed adversarial attack on the source domain. Then we did the cross-domain adaptation, which means we want a model trained on one domain perform well on MNIST. We performed adversarial attack on the target domain. Now, then we train both without just on applying on the source domain, without adversarial attack on target domain and adversarial attack on the target domain. Then we logged and experimented this. We got accuracy. We fine tuned on MNIST without and with adversarial examples. Trained with adversarial examples, fine tuned on MNIST, evaluating on MNIST test set, then evaluating the baseline and adversarial MNIST examples. So there we saw that here we saw that during the baseline training on Cypher 10, the VIT model achieved a loss of approximately 2.35 over 5 epochs. Following fine-tuning on MNIST datasets, the model loss decreased significantly, reaching approximately 0.15%. 0.15% here, okay. So, however, when subjected to adversarial examples generated the MNIST, the model's accuracy plumbed to 9.28%. So overall baseline model training and fine tuning has been done, where we got an accuracy of 14.38%, and then evaluation from here we got here 13 point approximately 14%. So here this one, the accuracy on the MNIST dataset, it was 73%. Adversarial training significantly so improved from models performance on MNIST tests. Achieving this, two we have got here 96%. Okay, and first it was 9.98% here, 9.28 per 9.98%. Here we got as 14.38%. So it was 9.98%. Later we got it as 14.38%. So this is a cross domain adaptive effectiveness we have achieved. The pre-trained on Cypher 10, it struggled to adapt the MNIST dataset during initial fine-tuning. Then it extended this training. So then, despite the improvement of general performance, the model's robustness to adversarial attack remained low. The baseline model accuracy on adversarial example was only 5.96%, and the adversarial trained model is 11.52 to 9.28. So here we achieved 11.552 here, and after this and all, so it needs basically more training. According to our observation, cross domain adaptation requires extensive fine tuning, as indicated by the gradual improvement in performance over extended epochs. Adversarial training significantly boosts generalization performance but does not fully address robustness to adversarial attacks. Then further epoch increase and training on different domains, we can increase the accuracy. So we have tried this model, we have done adversarial attack, and certainly we have improved some but not totally, but with a positive impact, with a positive mindset, we will carry on this project. And that's it. Thank you. to the, this is the quote I have example, to make the model more first.